I'll reply to your email very soon.
Yes.
I
was on the
Awesome. Let's get started. So today we are already at lecture 6, which is very quick. So today we're going to talk about sequential decision making, and we're specifically going to talk about Bayesian optimization, which is a really useful example of a lot of the principles of the stuff that Neil talked about last time. So we're going to make this again a lot more concrete. So if we think about the stuff we've really talked about through these lectures, right? So we had this philosophical stuff at the beginning, and Neil talked about Circes and all these nice things about stuff. What we really try to get across there is uncertainties are really, really important, right? If we want to learn, if we want to figure something out, we really need to somehow parameterize and think about our ignorance or our beliefs about systems. So uncertainties and probabilities is the language that we use to do this, right? So then I talked a little bit about statistical inference, of saying, how do we actually do this more mechanically or mathematically, of looking at building these probabilistic models where we can then parameterize what we know about the system and then do statistical inference to get an updated knowledge in the light of data, right? Mixing these two components. And then Neil talked about emulators. So when we have these scenarios where we've got these really complicated systems, and then we want to build these reasonably quick things around them that allows us to do experiments on them instead. So what we're going to do, what I talked about was these Gaussian processes, and we're going to use Gaussian processes as emulators. We're going to do one very specific example today that's going to exemplify this. So what we're going to do is we're going to talk about something called active learning. So we're now going to be in a scenario where uncertainties are going to be really, really, really important. So what do I mean by active learning? Well, we have some form of agent, right? So then we have some form of environment that the agent can act in. So now the agent performs one specific experiment, right? And now something happens to the environment due to the action that the agent performed. And then we get something back, we analyze this, and now when we've analyzed what's going to happen, then we will design and think about a new experiment, right? That's the notion that we want to do, right? So now, why is uncertainty then really, really important in this, right? Well, if you start off this loop, well, the first thing that we want to know is that I want to figure out how the world actually works. That thing looks very complicated. So now I have some notion of, I've quantified my ignorance about the world. So now I act according to that, right? And then something happens. Now I take the result of this, and I need to somehow update the knowledge that I have in order to do an experiment in a relevant way to keep learning something, right? Cool. So we've hammered this setting down quite a few times, right? And if you want to go the really long way, right, this is what we think about effectively as a scientific principle, right? All we've seen so far, we've done one step of what you most see in machine learning. We just do one step of this, right? You're having some data, pick a hypothesis, you get some updated result, at the end, you might predict something, right? Now what we're going to do is that we're really going to make the data collection loop part of the machine learning loop itself, right? And that's why uncertainties are super, super important now, right? It's not just saying, I have this data, now I do a prediction, this is how certain I am of the prediction. Now we're doing something much more richer, where we're saying, I have no data, I go out and gather some data, what does that teach me? Well, I don't know. Well, if you don't have uncertainty, you definitely don't know. If you have some uncertainties, then you get some updated knowledge, and then you can say, oh, I should probably ask this question now, right? So that's what we want to do. So we talked about Gaussian processes, and the nice thing now is that we have this. This is just some points that I've just fitted a very simple Gaussian process to, and I've plotted this thing that I said I hated, but it makes it a lot easier for what we're going to do now. Where I've plotted two standard deviations and the mean, right? But now there's one key thing that we didn't actually talk about, or I didn't make a big fuss about, really. So this uncertainty that we have here actually comes from two things. So you can split this uncertainty up in two ways. So there's two, if you look at the covariance function that we had, right? We had one ignorance that came from the likelihood function. Remember when we added the sigma squared I when we changed from F to Y, right? Remember this? That thing is the likelihood. That's the thing that says this is some uncertainty, that this is just the noise in the data. Effectively. It doesn't matter how many times I see this, I'm never going to learn anything more, right? I can't determine anything up. This is as high precision I can determine something in this location. And then we have the other uncertainty, which was in the covariance function itself, which says, this is what I don't know about the function. Now, the nice thing about the GP, the reason why I had like one slide where you said, oh, you can just add this term here, is because they're separable, like exactly like this. You can actually plot this exactly like this, where the red one is actually the noise, the green one is the added thing that comes from the thing we don't know about the function. So normally you're going to hear these words mentioned a lot if you read literature about this. So the whole field about quantifying different sources of uncertainty is called uncertainty quantification. And they like these two words, aleatoric or stochastic uncertainty, which is the randomness inherent in the system. Think about this as noise. So this is the measurement error that you always have. And then you have the epistemic uncertainty, which is related to our ignorance of the underlying system. And what we want to do when we do an experiment is that we want to reduce the latter. The former, it doesn't really matter, right? This is the stuff we can never ever get beyond this, right? If you have a specific measurement, if you have a ruler that measures a meter, if you've got a precision of a meter, you stop measuring, right? You can never ever get below that. So what I wanted to look at in this case here, if I said I'd split these two things into the green and the red one, now if we're going to make a decision about what points of this function should we evaluate to learn more about the function, in this case here, I have the possibility of seeing more data and reduce the green uncertainty. Well, in this case here, it doesn't matter, right? Because there's only noise left in the system. Okay? Cool. So what we're going to do today to exemplify this is that we need a task, right? So our task today is going to be black box optimization. So what this means is that we have a function that's explicitly unknown to us. So we don't know its functional form. However, we can query this function. So we have something where we can ask, what's the value at this point? But we can never ever get the mathematical formulation of the function, right? So we want to find the minima of this function. We're going to do this by building a surrogate model of the function itself, okay? So we're going to talk about how we can do this. And then we are going to design a sequential decision strategy such that we've seen some points of the functions. I've asked the question a few times, and then what's the most informative question to ask next, right? So that's the sequential decision strategy. And we're going to try and design it in the surrogate model that we have. Okay? Those are the things that we're going to try and get through today. Cool. So often this minimization problem is called Bayesian optimization. So you might have heard this. This is something that's incredibly useful. And it's actually one of the things that's actually generating money at the moment, which is kind of cool for machine learning. So it was even used for, it was a central part of the AlphaGo thing that I normally used to talk rubbish about, but this was actually the cool thing in AlphaGo, that they had exactly the stuff that we're going to talk about sitting on top of this thing, right? So they did something clever. Cool. So let's look at the problem then. So we have this function, f. We want to minimize this. We have a domain, which is the possible inputs. We're going to assume that this is bounded, right? Otherwise, it's going to be a little bit tricky. So this thing is bounded. Then the function f is explicitly unknown. So what I mean with that is I don't have the mathematical formulation for it. Okay? Evaluations of the function may be noisy, so you might have this uncertainty quantification issue where we don't know the noise, right? They might be noisy or they might not be. What we do know for sure is that evaluations of this function is expensive. What we want to do is evaluate this function as few times as possible, right? Cool. So an example of this would be an election, right? This is a really good example of this. So you got the US here, colored in, they use the different coloring than we do here. But let's say that we want to form an election, or actually we want to estimate how people would vote in an election. So we want to do an election poll, right? So we don't know, if we have the function of how people would vote, it would be super easy, right? We don't have the function, so we need to go out and query people, right? The simplest thing to get the right answer, right, is to just ask everyone. Then you have the perfect poll, but you've also run an election, right? So we don't want to do that. So now the strategy that we should think of, which people who generate polls do a lot, right, is thinking, how do I get as low uncertainty as possible about what the result of the election will be by asking as few people as possible, right? And now what you don't do is you ask just everyone that lives down here, if you've got 10,000 calls to make, you probably think a bit more cleverly about how you do this, right? Okay, so that's effectively our setting. You can think of this, even though this is probably really, really hard to do. Cool. So let's see what the worst things you can do. What's the thing that we could beat, right? So let's say that we're going to do random search. So we're just going to ask people, I'm just going to pick up the phone and just randomly call people. But what I'm going to say is that I want to find the best minimum of this up to an epsilon, okay? So I have some epsilon error where I say I'm okay as long as I'm epsilon away from this. And then I'm going to make another assumption of my function. I'm going to assume some smoothness of the function. So we're going to assume something called, this is, if you haven't seen this before, it's referred to as Lipschitz continuity. So the only thing it really means is that if I move this much in the input space, the function value can move c times that, right? Okay, so that's effectively used the smooth, or the other way around, sorry. Yeah, 1 over c times that much. Yeah, sorry. So a very large c is a very smooth function. Okay, cool. So if I would do that, and my input domain is d-dimensional, and I take the input space and I shrink it to a cube. So you scale it to be a cube, 1, 1, 1, 1, 1, right? A unit cube. The number of evaluations that I would have to do to guarantee that will be c over 2 over epsilon to the power of b, right? This is a lot of evaluations if the space goes and if the function is not very smooth, right? So that's the worst thing we can do, right? So that's what we want to beat. Now we want to be a little bit more clever, right? So we made a very weak assumption about the function, and then we can say something like this. Okay? Great. So what we're going to do instead is that we are going to implement the surrogate model and try to use that to guide our search, right? And now we can take all the stuff that we've learned so far of saying, do I know something about this system? Well, actually, I'm going to put all the knowledge I have into this, and I'm going to exploit that to beat this. That's the aim. Okay? So we're going to use Gaussian processes for this. And why are Gaussian processes useful for this? So there's a bit of a strange thing when we look at Gaussian processes, or when you introduce Gaussian processes. So when we looked at these plots, where I sampled things from these, one of the things that people often think, I thought the first time I saw them, I thought, wow, this is amazing. What an enormous diversity of functions, right? It looked like it's like lots of different functions in here. No, it's not. It's the other way around. Actually, if you looked at those functions, you remember, I should have really had a plot, but you remember now you've generated them yourself. You took this squared exponential kernel, they looked all over the place, but they looked exactly the same. They all have exactly the same characteristic, right? They were all smooth. They were just covering lots of parts of the different space, and they were weighed in different places, but they were all exactly the same weight, right? Do you agree with me on this? Nod heads, please. Good. I see lots of nodding heads. So actually, it's a super narrow prior. It's used that in our minds, we often think about parametric models, right? And we say, oh my goodness, if I would have to parameterize all these functions, it would be like the biggest, most general function I would ever think of writing down, right? But actually, GPs are super narrow, right? As soon as we specify this, and this is good, because what this means is that we can put a lot of knowledge in, and because we have a very strong prior, we can then learn very quickly, right? Cool. The second thing, which is really, really useful, is they provide a belief over the whole domain. If you see these points, you can say at any location, any continuous location, you can get your updated belief, right? This is super useful, right? So weirdly, if you see something, you now have a quantification of your uncertainty of everything. And that's really, really useful, right? Yeah.
On the other hand, when having very narrow priors, like while it does allow us to insert a lot of knowledge, doesn't it also kind of require us to have a lot
Exactly, it does. It does. Completely agree with you. It really does. However, my argument for why that's beneficial is that I think in terms of machine learning, we're much more common in the situation where we have a lot more knowledge than we can use. For most physical systems that we look at, what's the limiting thing is that our knowledge doesn't really fit with these handles of input in them, and they really don't fit into covariance functions either, right? But if we work on that, we can put more knowledge in, right? Okay. So I think, yeah, it is a benefit that you can, right? Cool. So what I'm going to do first then is that let's just do a random search. So to just see what we're going to sketch, what we're going to try and do. So throughout the rest of the talk, I'm going to use exactly this example. You're also going to do a lab on this example or a worksheet on this example. So you're going to get really bored of this example. This example is used a lot. You can see it has two minima. So it has the local minima. That's the tricky part of this function, right? So the plots I'm going to show is all going to be of the same type. I start off like this. I have not seen the black function. The black function is unknown to us at this point. Then I've specified a prior belief, which is symbolized by this blue Gaussian process prior. And then I'm going to give you one point after the other, and we're going to see how we update our knowledge about the minimum. Okay, so I'm just going to start off by showing the simplest thing of this being a random search. So I'm just pulling X values randomly to show how my belief get updated. So we start off with these 2 points, and then what you can see, right, is that with this covariance function, it's very simple, right? Effectively, it says my knowledge, it falls off with the square of the distance between 2 points, right? So it seems a bit silly then to do random search to try and find points. So let's be a little bit more clever and instead start off with these 2 points And then we are going to continuously ask the question greedily where my current belief is where the minima is. Right? So I'm going to take the min of the mean and add that in the whole time. Right? Okay? We happy about this? Good. So I started off with these, then I added this. Now, of course, that one was very high. So now the mean gets pushed up over there. Now we pick this one because everything was on a slope. So it thought it was over there. Now I pick this one. Dunk, dunk. And now we're stuck, right? So if I keep running this, I think I'm just going to sample there, right? Do you think this is a sensible strategy for searching? No, it's like an utterly stupid way of searching because, well, no, it's not. It's what I do when I hunt for biscuits in my kitchen. What we're not exploiting here is that we're not exploiting how we quantify what we know, right? We're just using the minima of the mean the whole time. We're not saying anything about how certain I am, right? So actually, there's a thing which I think we often do when we search that I'm now going to try and explain. So I'm going to try and explain this through my favorite thing, beer, right? So this is my classic example. Eventually, I'll try and exchange it to cycling, but we'll see. So if you enter a pub, right? A good British pub will have lots of beer on draft. And now you have a challenge, right? Because your task, right, is to find the nicest beer. So now some of them you've had before, and some of them you haven't, right? So now you need to come up with a good strategy, right? So I'm going to simplify this even more. If you never had a beer in your life, you're humanly engineered to like sugar. So now sugar is nice, so you'll pick a Coke, right? Great. Now, what you will continue doing, you like this, you'll just continue drinking Coke. However, I'm telling you, you're missing out on this fantastic Y Valley bitter if you're stuck in that point. So what you need to do is move out of your comfort zone and do a bit of exploration. However, you can't explore too much because I found this on the internet. So what you need to do is you need to balance these two things, right? You need to bring yourself out of the comfort zone to do a bit of exploration to find other good parts, but you can't explore too much because this is bad. You also need to do some exploitation. So after you found one that's good, well, maybe you have two, right? Cool. So this is the concept which is really important in learning. That is exploration and exploitation. I also think of this as if you're preparing for an exam, right? So in the beginning, now there's like months till you have to write exams, right? So you spend the time doing a lot of exploration. You might pick up the things, oh shit, I didn't go to that lecture. I'll do a bit of exploration. You test the stuff that you think you don't know, right? 4 hours before the exam, what do you do then? Well, you memorize the questions that were on the previous year's exam, right? You do exploitation, right? So a good sequential decision strategy has to balance these two terms, right? And now we're going to try and see how we can do that with the surrogate models that we built. Okay? So let's look and try to use the uncertainty of this. Because all the things, right? The things that we need to do this strategy comes from all the arguments that I did came from saying, oh, I know this, I like this, oh, I'm uncertain about this, I might like this, right? So you have to use your uncertainty to think about this. So what I'll do here is that, same plot as before, I've taken these 4 points, and what I'm going to do now is that I'm going to draw samples from this Gaussian process hysteria, and I'm going to plot the minima of this, right? Of each sample, okay? So I've sampled this one, the green point is the minimum. Sample another one. That one says the minimum is probably here. I sample this one. Dunk, dunk, dunk. Let's see, there I stop. So what you can see now is that each one of these, drawing a sample of this, respects your knowledge about what you think of the function, right? These things here are definitely not randomly distributed, like they're not uniform randomly distributed, they're random, right? You can clearly see a structure of these, right? There's a lot of them here, quite a few of them more in the beginning and towards the end, and right in the middle, right? Would this be a sensible structure to actually search this based on? Right? Cool. So let's do that. And this is an approach called Thomson sampling. So what we'll do, what we'll do, I'll come to the equation in a bit, is that I'll now walk through this loop. And what I'll say is that I'm going to draw a sample, and then at each location, I'm going to take the minimum of that sample, and I'm going to include that point, and then I'm going to fit my DP again, and I'm going to draw another sample, and I'm going to keep iterating like that. Cool? So the green bar shows where the minimum is. So 2 points, drew a sample, pick the minima, and we add the minima. Now, clearly, all these things have been pushed up. So now we draw another point here. We add this in. This one's a funny sample, right? But I'm used sampling, right? So if I didn't set my random number to be 42, which I always do, then it'll be something else, right? Cool. Dunk, 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 right? So this seems to be a search strategy that much better represented the knowledge of how I knew the things I had, right? Do we agree with that? Cool. So, got a little bit out of phase of my slides. So the way we're going to do this in general now is that we're going to think about formulating a function which we're going to call the acquisition function. And the acquisition function is the function that's going to tell us where should I query the problem next, right? So we're going to call this function alpha. It's a function over x. It takes the current data that you see and your current surrogate model at this point, which I call MN. And then we are going to, weirdly, we're minimizing the function, but we're going to maximize the acquisition function. Okay? So we're going to take the point of this, which is maximized, and then we're going to add this in. Okay? Cool. So in this case, the acquisition function is just the negative sample of a function, if you want to. But let's think about it a little bit more cleverly. So here is an acquisition function called the upper confidence band. So we want to balance exploration and exploitation. Exploitation comes from the mean, right? When we started off using the mean and adding the minima, we said we were just exploiting. The exploration goes from, say, going to a region, oh, the mean might not be really good here, but I'm really uncertain. That's exploration, right? So if we take the mean here, and then I take the variance, and I just put a scalar factor between them, right? Now I'm effectively, by this parameter, balancing exploitation with exploration, right? So the way this looks here is that I've plotted in magenta the acquisition function around this, and then we have exactly the same thing with the graph above. So let's walk through what this does. So first case, I have these 2 points. Now this here is the maximum of the acquisition function. I'm going to add this point in, Bonk. Now you can see this thing here, two things happen. First, the variance shrunk, right? So it's less beneficial to explore it, and the mean went up. So it's less beneficial to exploit. So this thing here kind of disappears. I've cut this function. It doesn't go down to 0, you can see, but this is how this one looks. Okay, so now we've got this massive thing over here. So we're going to pick the max of that. Bonk. And now it splits up into 2 parts or 3 parts. This thing here, because that point was so high up there, this thing is a little bit smaller than this one is here, right? Okay, so then we go and explore or pick the one in the middle. Bonk, donk, 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 donk. Now, the problem with this one is, well, are you happy with this strategy? What happened now? I can tune this beta parameter, but would you really, at this stage here, go in and query stuff over there? So the reason for this, I've set these parameters the wrong way to make my slides look really good. But look at this strategy here. Wouldn't you want to go over there and do a bit more of exploration with 1 point rather than sampling this so closely? So what we're going to try and do now is that we're going to try and come up with a different function that allows us to do that slightly better. Okay? Dunk, dunk, dunk. So effectively, we can come up with loads of different heuristics for doing this thing. Like in the previous case, what the hell was that beta parameter? I don't know. If I alter that beta parameter, it's going to be different every time. So one way of defining acquisition functions a little bit more principally is to think about the utility. Okay? So what we now say is that we say that the utility, we specify a specific utility function. What is the value for me seeing a specific value? And then we define the acquisition function as the expected utility. So what that means is that we say, specify a utility function, then we have a belief over the function, right? Our surrogate model, and then we integrate that. And then we have an acquisition function. The first one of these I'm going to show is something called the probability of improvement. In this case, what we say is that if I believe the function is worse than my current best, it has no utility to see it at all. If it's better, it has the utility of 1. For this one, if I compute this integral, it's very simple. So the only thing you have to do, remember, the utility is 0 for anything that's worse than our current best. So you start off with the GP. Remember, at every marginal, you have a Gaussian. Whoa, right? Now you effectively say, I'll cut that distribution at the best value that I currently have, which is the cumulative distribution from -infinity, look up to that. That's your acquisition function. Yeah? So if we look at that, you can kind of see this. I've effectively cut that blue thing through the red point, taken that blue variance and just flipped it around. That's my alpha value. If I do this, chop, 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 going down here. Okay, so one of the things with this function is that it says that the utility of being a minuscule part better and believing that you're miles better is equal. Maybe that's not a very sensible strategy, right? Maybe you want to say, I really think I might be tons better over there. You should prefer that to something that you think is a tiny bit better, right? So we can do that with this very simple acquisition or utility function, where we say we're now going to look at the utility is proportional to how much better you think you are, right? If we compute this, don't worry about What I wanted to just show, the thing you really have to see with this thing is that you've got two terms. You've got the CDF of the Gaussian proportional to how much better you think you are. So, and then you got this term here, which is just how much variance you think you have at this place. So it balances, it has two clear terms, one that's exploitation, the red one, and one that's exploration, which is scaled by the variance at that point. Okay, this is the one we're gonna, which is probably most commonly used, and it's the one we're gonna use in the lab, right? So if we do this one, start off looking very similarly, we always seem to go out in the far right. Dunk, 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 dunk. I think this is an, did I include another? Yeah, there we go. And it goes out here. This is the big difference that we had before, because now I have a lot of variance left over there, and now it's happy and start in that place. Yeah. This one here, I think looking at that, I'm really wary of if I have a loop counter in my code that because it clearly shouldn't be doing that. That's why I try to hide that and jump off the previous box. I would be very surprised if it ever did. It shouldn't really do this one. So I'll have to update code that does this, even though it doesn't seem to go exactly through it. It shouldn't. If you look at that equation, that shouldn't happen there. So I wonder if I'm plotting this one from the previous iteration or something. I'm not sure. So sorry, I'll remove that slide. But that one should be there, and then you can kind of happily see that one. Yeah, we happy about this? Cool. You'll try this. If you get that same error, then there's something very wrong. Yeah.
So you said that, you know, if we're expecting the variance to be high, then our function will let it go there, and that's expressed by the k and x.
Yep.
I guess that's the uncertainty related to like kind of microvariance, a potential function
Yep.
to describe data, not the I guess the get the word used.
Oh, the aleatoric epistemic thing. Yeah. So in this case, you can see right. So you would have you can have two terms there, right? So when we wrote down the covariance function, we had k plus this thing. You wouldn't do this based on the noise, right? So that k is just about. However, how do you estimate the noise? If you don't know the noise, you might have to sample this to get an estimate of how much noise you actually have, right? But in this case, we are completely noise-free, right? Cool. So I could go on about showing you all sorts of different strategies and all sorts of different functions here, but I don't really want to do that. The reason why I showed you lots of them was for you to see strategies and just get used to exactly what we were doing, right? And hopefully, what you think is that it kind of makes sense, right? Don't worry about how the equations for the acquisition function look like, but it kind of makes sense to balance these two things, right? And when you think about that, you have all the information in your Gaussian process, right? Because you have the uncertainty at every point, and you have the mean estimate at every point, and now it's just about balancing them to figure out a good strategy. So let's walk through what we did for several different cases here now. So what you begin with is you encode your knowledge about the function in the GT prior, right? You figure out as much as possible you know about the function that you're looking at. So you encode that in the GP prior. Then you start off by randomly picking some points, right? Boom. Then you specify your acquisition function. Now you evaluate and maximize the acquisition function. You go out and add the data points, and you might re-estimate your hyperparameters based on this of your surrogate. And then you keep doing this until your budget is gone. Or in my exam example, when you really have to go in and write that exam, you stop, right? Now you just exploit, right? So that's effectively the loop that we're going to go through. And hopefully this kind of summarizes or exemplifies a lot of the things that we've done, right? So we said this thing where you start off and you think that if I want to learn about something, I have to exploit the knowledge that I have to figure out all this stuff. A GP is a decent handle for inputting a lot of these things. Then you see some data, you update the knowledge that you have, and you keep exploiting this, right? Cool. So, do we got any questions on this now? No? So, what we're going to do is that there's a worksheet on this thing that is here. And you are going to walk through and do this here is going to be very similar to the thing that we did during the lab. So you're going to implement this thing. Then, so far, at least in all my worksheets, you've coded everything on your own in NumPy because I really want to show how simple these things are, right? When we coded the GPs, sure, you could pick down a library, or you could have written 3 lines of Python, and now you see how simple they are. Now we're kind of getting to the boundary where it starts being useful to use other people's code. We're going to do this one, but then we are going to use a toolbox to do some more interesting things. So Neil talked about GPy. There's this other toolbox, which also which Neil and Javier and lots of other people have worked on, which is also part of EmuKit, or underlying parts of EmuKit, which is GPyOpt. And GPyOpt implements Bayesian optimization, but it does all sorts of cool and clever stuff. So what we're going to do is that we're going to do a much more complicated function where we might have some more knowledge. We're going to look at this function. So this function has periodicity in 2 levels. So there's 2 different periodicities. There's also a linear trend going on. I'm telling you all this stuff, and now we're going to try and exploit that. What you're going to see, and this comes back to your question up here, if I don't exploit this knowledge, you're going to get results looking like this, right? This is me just saying I'm going to put a squared exponential, the same smoothness, and I'm going to get results looking like this. It's not searching particularly cleverly. If we exploit this knowledge, instead, we exploit this knowledge, you're going to see something much more cleverly like this, where I actually know some parts of the periodicity of this thing, and then we're going to. My toy example here is this is some planet that have a daily rhythm and a yearly periodicity, so I can actually know quite a bit about these things, right? Now you can see the search on this is about figuring out the periodicities, but as soon as you've figured out the periodicities, you're kind of good to go. You can just go to the minimum, right? So, but to do this, we're going to use GPyOpt to do this, and it does some more clever things internally as well. Cool. And then the final thing is that we told you that we were aiming to do some form of individual assessment of this. So what I've done, so we're going to put this up today, that I've made this lab, but not the last bit, as a, well, I figured out you can run Jupyter notebooks in Emacs, which made me very happy. So that's the only reason I now have generated a Jupyter notebook. But what I've done is that I'm going to just put up this. And the thing we're going to do is effectively implement the parts of the PDF. And then there's a couple of additional experiments, right, in here. And then we put a deadline for the 4th of November to submit this each individually, right? So that's just walking through the PDF and running a couple of additional experiments on this thing. Yeah, we happy about this? Any questions on that? So you're used to doing the first experiment, but I really recommend to run the deep opt experiment as well, because there it starts getting a little bit more interesting, right? Cool. Okay, do we have any questions? Yeah. So we said that I'm gonna do one, which is this, and then Neil's gonna do one as well. And we're gonna say that each them together is 50% of the mark. So, however, because we messed up, you're not going to see those as two individual marks. They're going to be one. So we'll let you know. But yeah, that's how we have to work. Cool. Do we got any questions? Yeah.
For the randomized,
Yeah.
It's a similar balance for testing.
So again.
Is it balance for the effect?
So no, because you can't actually know up to, it's a very good question. So maybe I'll try and rephrase it. So can I get any guarantees on the optima that I get? Absolutely not. Right? So this is the tricky thing. You can't, right? So you can only make, if you make an assumption, if you don't make a Lipschitz assumption, you can't say anything, right? Because the function can vary arbitrarily quickly. If you make a Lipschitz assumption, that is going to give you a bound, which was that bound, right? But then it doesn't say anything else for me doing that search. Yeah.
Is it certain that if you get both this model is optimal, they have like two tries that should you maybe consider both that community?
Awesome. Yeah, you probably shouldn't do a greedy approach, right? You should be more clever about this, but this is really hard. This is really hard. How do you think about these strategies for not doing it? And thinking about higher order ways of doing this. Another thing, like there's so many moving parts in this thing, right? Think about the two random points I always started with. One of the experiments you're going to do is alter those random points and see how your search changes. It changes massively, even for that simple example. So yeah, it's a really, really tricky one. So what we're going to do in the worksheet is that you're going to look at the variance over multiple runs, right? Because there's a lot of stochastic parts in this, and what you really want, or a trade-off, is a method that has a really low variance on the output of making multiple runs. You can kind of trust that, but then what you often see, you might have other methods which has a huge variance at the end, but they get really good results now and then, right? So what's the balance of doing these things? Super tricky things, and there's a lot of open questions in this area. And effectively, if you think about it, the whole acquisition function stuff is a little bit of a hack, isn't it? Right? I motivate, oh, the utility of this is potentially this, that, and it's great. There's a lot of work to be done, right? Multi-objective things, stuff with constraints. There's lots of stuff to do in VO. Great stuff to do for projects, great stuff to do for individual projects. Yeah, more questions? Yeah.
So can you say one more time on the Lipschitz continuity, just like assuming like some sort of boundedness and compact constraint?
Yeah,
It doesn't with this method fail, like some hole somewhere, effectively when function dips.
Yeah. Let me show you a simple example. So this is from a student, former student of mine. This is some work. So here you've got a function which looks like this. It has these, very sharp changes in certain regions. Now, in this case, yeah, so the search here becomes really, really problematic if you end up finding something here, because you'll estimate that the function is varying super, super quickly, and you'll be very uninformed about this region, right, which is far away from the middle. These are really troubling things with the strategies that we develop. However, again, it's a lack of knowledge. If I know something of this, maybe I can put it in. Say, for example, I got an engine that I optimize. And I know at the very low RPM, it's going to shake a lot. And then it gets like, whoa, it gets into the zone, and then it starts stabilizing up. And I know I'm looking for something in that zone. Maybe I can put that knowledge into the system. Yeah.
Is that true even in higher dimensional settings? Like this is 1D. How does this scale?
Yeah, so it doesn't scale. So it becomes very tricky in high dimensional spaces. Reason for that is because in this case, the covariance functions that we use, and most of the covariance functions that we do use, is based on some form of Euclidean distance, which loses information when you get really high dimensional spaces. So you effectively start searching randomly very quickly because your DPUs becomes like this very quickly. We need to dash off, but I'll be outside and chatting after this. Yeah.